All right, let's talk about something that is happening all around you right now, probably dozens of times a second. We're going to crack the code on data encryption. It's basically the invisible shield that protects our information every single moment we're online, and we're going to break down exactly how this amazing technology works. Okay, let's get into it.
I mean, just think about it for a second. Every time you click buy on a website, your credit card details literally zip across the globe. Or you send a private email and it bounces through who knows how many servers to get there. So what's stopping someone from just, I don't know, grabbing that information right out of the air? And, that's the scary part. That is the real risk. Our personal, valuable data is constantly flying around, and yeah, there are absolutely people out there actively trying to snatch it. They want it for fraud, for identity theft, you name it. This is the fundamental problem that all of digital security is trying to solve.
So, what's the solution?
Well, it's this really clever idea called encryption. It's not about building some kind of unbreakable digital wall around the data. It's actually much smarter. It's about making the data itself completely scrambled and useless to anyone who isn't supposed to have it. So let's look at the basic pieces of this puzzle. So first up, you have what's called plain text. It's exactly what it sounds like. This is your data in its original, easy-to-read, understandable form. It could be your email, your password, your bank details, whatever it is, it's the stuff we need to protect. And then, once encryption works its magic, that plain text gets turned into what we call ciphertext. It's just a complete jumble of nonsense, a meaningless string of characters. Now, if a hacker gets their hands on this, they have no idea what they're looking at. So what's the secret ingredient that turns the readable stuff into the scrambled stuff? That would be the encryption key. You can think of it like a super secret recipe or a really, really complex set of instructions. It's an algorithm that tells you exactly how to scramble the data in a very specific way. This key, it's the secret to the entire process. So when you put it all together, the process is actually pretty straightforward, at least on the surface. You start with your readable plain text. You use an encryption key to scramble it into ciphertext for the journey, and then the person on the other end uses that same key to unscramble it right back into plain text. Simple, right? But what does that really achieve? And this is such a crucial point to understand. Encryption is not some kind of force field. A hacker could still technically intercept the package of data, but, and this is the whole point, because that data is now ciphertext, it's just gibberish to them. They might have the locked box, but they have absolutely no way to open it. Okay, so with that in mind, let's look at the first major way this is done. It's called symmetric encryption. And the name kind of gives it away, right? Symmetric means balanced, the same on both sides. It's all about using one single key to do both jobs. So with the symmetric method, it works like this. You use one secret key to both lock the data and unlock it. The sender scrambles the message with the key and sends the scrambled message on its way. But they also have to find a way to send the key to the receiver, usually in a separate package, so they can actually unscramble the message. And right there, you've probably already spotted the huge glaring problem, haven't you? It's like sending a locked treasure chest in one delivery truck and sending the only key that can open it in another truck right behind it. If a clever hacker manages to grab both trucks, well, the lock is totally useless. They've got the box and the key. Game over. So, that critical problem, how do you safely share the secret key, is exactly what led to a much, much more secure and brilliant solution, asymmetric encryption. And again, the name tells the story. It's asymmetric, it's unbalanced, and that's precisely what makes it so incredibly powerful. So let's put these two side by side because the difference is everything. Symmetric uses that one single shared key to do everything. Asymmetric, on the other hand, splits the job into two completely different but mathematically linked keys, one called a public key that only locks the data, and a separate private key that only unlocks it. Let's see how that works in the real world. To really make this click, let's ditch the abstract terms and just imagine a simple scenario with two people. We'll call them Tom and Jane. Tom wants to send a secret message to Jane. Okay, first things first. Jane, the person who wants to receive the message, creates her own unique pair of keys. One is her public key. She can share this with absolutely anyone. She could post it online, shout it from the rooftops, it doesn't matter. But the other one is her private key, and this one she guards with her life. It never ever leaves her possession.
So Jane sends her public key over to Tom, and this is completely safe because, remember, the public key can only lock things. It has zero ability to unlock them. A great way to think about it is like she's giving Tom an open padlock. Anyone can snap it shut, but only Jane has the one unique key that can open it again. So Tom takes his secret message, his plain text, and he uses Jane's public key to snap that padlock shut. Click! He scrambles the message into ciphertext. And here's the really cool part. Once he locks it, that message is sealed for good. Not even Tom, the person who wrote it, can open it back up again. And now, Tom can send that locked message out into the world without a single worry. If a hacker intercepts it, it's no big deal. All they have is a locked box. The public key that locked it is totally useless for opening it, and they don't have the secret key because it was never sent in the first place. Finally, the locked message arrives with Jane. She just takes out her secret private key, applies it to the scrambled message, and voila! The padlock opens and she can read Tom's original message. Her private key is the only thing in the entire universe that can open messages locked with her public key. The secret was never at risk. It's brilliant. Okay, so that's the mechanics, Tom and Jane, public keys, private keys. It's a neat system, but where does this actually show up in your day-to-day life? Well, the short answer is absolutely everywhere. Every single time you log into your online bank, you are using asymmetric encryption. Your bank has a public key that your web browser uses to lock up your login details and your transaction requests. Then, the bank servers use their secret private key to unlock them. It is the fundamental technology that makes secure digital finance even possible.
All right, let's just quickly boil all this down. The key takeaway is that encryption is all about scrambling our data so bad guys can't read it. The old school single key symmetric method is simple, but it has that big security flaw. It's the two-key asymmetric system with a public key to lock and a private key to unlock that has become the absolute foundation of our secure online world, from shopping to banking to just sending a message. And that kind of brings us to a final, pretty big question. The encryption we rely on today is built on math problems that are just way too hard for our current computers to solve. But what happens when computers get a whole lot smarter? As we head into the new era of quantum computing, we might have machines that can crack these codes in seconds. The race is already on to invent the next generation of unbreakable digital locks for a very different kind of future.